Here are the sets I'm going to define. We'll define the universal set. And this is just a particular example, so you can call this example. Okay. We'll define the universal set as all of the integers from 1 to 30. Okay, all the counting numbers. 1, 2, 3, and so on. By the way, just as a side note, if you ever define a set like this, right, and you want it to follow a pattern, you need to have at least 3 numbers in here to start off your pattern, right? 1 number obviously is not enough to establish a pattern, but 2 numbers isn't enough either. Can anyone suggest why? Like if I had said just that, why would that not be enough? Yeah. Good, that's right. If I just said 1, 2, you don't know whether I'm adding or whether I'm multiplying, right? So there's ambiguity there, right? So to get away from ambiguity, 3 is kind of a normal number, okay? All right, so there's our universal set. I'm going to define set A to be the even numbers that belong in here. The even numbers. So we'll just write it like that. Or if you like, the multiples of 2. Set B, I'd like us to define it as the multiples of 3. So we're thinking about, this is our playground, 1 to 30, okay? Multiples of 2, multiples of 3. You're going to start off your diagram. Here's the universal set there, okay? And we've got A and B, and there's some overlap between them, okay? So, easy example. You start with the first one, 1. Where does it go? Is 1 a multiple of 2? No. Is it a multiple of 3? No. But it is in the universal set. So I'm just going to stick 1 down here. Okay? 2. Where does 2 belong? 2 belongs in A. Does it belong in between? No, because not also a multiple of 3. So it has to be in there. 3 obviously is going to be here. You can go from there. Okay? I'd like you to fill in all those numbers. I'll give you a couple minutes. So we've got our multiples of 2 over here, our multiples of 3 over here, our double ups, and then our ones who don't belong. Okay? Now, let's have a look. Once you've done this, do you observe any patterns? Right? The most obvious pattern that jumps out to me is if you have a look at A intersection B, right? There's a very easy way to define A intersection B without saying A intersection B. It has its own quality about it. What is it? They're the multiples of 6, right? Multiples of 6. Okay, so when you take intersections or unions, that kind of thing, you get new properties sometimes. Now, have a look at the other ones. For instance, what about this area over here? How would you define that? How would we write that in set notation? Just this area, here.
Oh, not A minus 1B.
You can say it a couple of different ways. You could say, well, I don't want A, right? But I want B. So I would probably say I start with B, and then I want to get rid of A. Right? I think that's probably the easiest, most succinct way to say it. Like I said, many ways to skin a cat, okay? Well, what do you notice about these particular numbers over there? I mean, obviously they're multiples of 3 because they are part of set B. But what kinds of multiples of 3 are they? Yeah, of course, because when you think about it, look, you've got, this is 1 times 3, right? That's 7, and then 3, and then 5, and then 9. 1, 3, 5, 7, 9. Well, of course they have to be the odd multiples of 3, because all the even ones are in here, right? Anyway, you can keep going. Now, here's my point. This diagram, it's a helpful way to see things, but it's not the only way, okay? I want you to think back to when we were doing, do you remember when we were doing the 4-color theorem? Okay, and we had a look at maps, okay? Now, you might want to draw this up quickly for you. If I gave you, 3 countries like, make it a bit weirder, so like that, and something like, suppose that's like Italy or something, I don't know. Okay, so if I gave you a map like this, okay, I very, very briefly mentioned the idea at the end of the lesson that from a topology point of view, right? Which is thinking about these spaces and how they relate to each other, how they fit together, right? All of this jagged business, I don't really care about it, right? I could say that this is kind of equivalent to, well, I could round this all off. I could draw it like this, I think. Let me look at it. Sort of like this. Would that be, I think that'd be sufficient. that make sense? I mean, have a look at this one. It borders these two. Okay, so let's call this A, B, C. A, B, C, right? So A borders B and C. Sure. B borders A and C. It works, okay? These two are, from a topological point of view, they're equivalent. And I could go one more, you know, who says it has to be round. It doesn't have to be round. I could draw it like this. I could do it like that. That'd be still the same, right? You got the same concepts there. Now, you can see with our Venn diagrams, right? Why are they circles? Why is this a rectangle around the edges? Well, for not any particular reason, really. Venn, the guy who designed this, he was very keen on symmetry, right? And so that's why he's like, circles, the most symmetrical shape ever, right? Infinite, you know, reflectional, rotational symmetry. So that's why he was very keen on circles, right? But they don't have to be, okay? So, rub off all of your countries, okay, well no, not rub off, rule on off, and then underneath them, let's think about this. What would be another way to represent this same number of sets? Are there any better ways? Now, I'll give you an example, okay? There's literally an infinite number, okay? But I could say, well, this is kind of equal to, if I wasn't constrained to make these circles, okay, I could say, well, around the edges, I could make one kind of like an oblongy sort of shape, and another one which is kind of oblongy over there. And do you agree that this is still, from a topological point of view, this is still the same, right? I've still got a universal set, only A, only B, and an intersection. No problem. But then I look at it, I'm like, I can make this simpler. I can make this simpler. Look at all this space over here. What is it doing? And the answer is, on our diagram, well, it's not really doing anything in particular, right? It's not doing anything that this space, this region, is not also doing. So I can kind of get rid of it. I can say this is, I'll go this way because I'm running out of space. This is equal to, now can you imagine if I took these and I sort of melded them to the side, okay? So here's one of the circles which I squeezed and I squashed. Let's regather. Shh. So we said, here's A and here's B, right? Morphed a little bit, here's A, here's B, all still good, right? Now, at least in this case, I've taken this taller one, I've moved it over there, and I've pushed it up against the side. But I'm still okay. I'll call this B, right? Now, where would A go? Well, if I move it down to the bottom, it would look something like this, wouldn't it? There's A. Okay. Now, hold on a second. Does this look the same as this? It's starting to look quite different, isn't it? But it's still the same. It retains all the same information, which is the most important part. I'll tell you how I know. In this diagram, right? Let's think about maps and four-color theorem. How many separate, distinct regions are there? I know there are two sets, but there are four. 1, 2, 3, 4 regions, and you can name them. You can name them. You can call this one. Well, this is kind of, there's nothing in it, right? You can call this one A and not B. You can call this one B and not A. And then this one in the middle, of course, is intersection. Okay? Well, over here, I still have the same 1, 2, 3, 4 regions. And to make sure you haven't lost any, you can name them, right? Have a look at this one. That's the empty one, right? Over here, you've got A and not B. Up here, you've got B and not A, and then you've got your intersection down here. Okay? So, let's formalize this. Let's get rid of all of our curviness, right? And let's just draw this like what it looks like. This is a table, right? I'm going to draw it, I'll do it right up here. I'm going to draw it like this. Okay, like so, right? Now the reason why I've got these extra bits off the top is so that I can label what these actually mean, okay? So if I call this one up here, let's call this one A and not A. Okay, so even numbers, not even numbers. Call this one B and not B. Okay. So now, where would the numbers fit? For instance, these numbers out here in the universal set, right, which don't belong inside, where did they go? They're going to be, yeah, good. It's going to be over here, right? The you guys don't belong. Sorry. Okay, so I'm going to put all of these guys here, 1, 5, 7, 11, 13, you get the idea. All belong down here, okay? In not A, not B. Conversely, I can take the opposite of that, the intersection, A and B, right? And that's going to be these multiples of 6 we talked about, right? 6, 12, 18, 24, 30, okay? And you can fill in from there, okay? And I'd like you to do that. Now, as you're doing it, you can label it. You know, you've got a Venn diagram down here. This guy up here, the guy who formalized this and saw, this connection, I can do this differently. There's a guy named Carroll. So we call these Carroll diagrams. Now, he wasn't just any Carroll. Just think, there are not that many famous Carrolls that you might be aware of. How many Carrolls can you think of that you learn about? Yeah. Lewis Carroll. Lewis Carroll of... Why is Lewis Carroll famous? What did he write? He wrote Alice in Wonderland. Right? Now here's the thing. Lewis Carroll was not just an author. He was a mathematician. Now maybe you didn't know that, but Walt Disney knew that, which is why when he did not Alice in Wonderland, but Donald in Magic Land, which you watched a couple of weeks ago, right? Alice. You might have even noticed, those of you who were keenly aware, there's a scene where they're starting to talk about all these different games. I think it's after the music. He looks through billiards, he looks through checkers, he looks through chess. And then suddenly, if you were paying attention, Donald, he gets a new outfit change. He's dressed up as Alice in Wonderland. Okay? And in fact, if you go back and read Alice in Wonderland, it's full of maths, especially its sequel, Through the Looking Glass. So you can go and have a look at that, Lewis Carroll. Okay? So we've got these two ways of representing sets and how they relate to each other. And as you will discover in the next couple lessons, they each have their own particular benefits.